Okay, guys, today we're looking at simple harmonic motion. We have seen periodic motion before, just motion that repeats itself over equal time intervals. But what's really interesting about simple harmonic motion, simple doesn't mean that it's the easiest kind. It just means that there is a simple way of describing the position, velocity, and acceleration of an object in simple harmonic motion. So for anything that's in simple harmonic motion, the position, velocity, and the acceleration is all going to be described by either a sine or a cosine function. And in order for that to be true, to be in simple harmonic motion, it means that there must be a linear restoring net force. So we'll take a look at what that means on the next page. Okay. So we have to imagine a situation where there's no friction or drag. And if that's true, then we could get simple harmonic motion with something like a pendulum that swings back and forth, or like this spring mass oscillator right here. But if we have friction, then unfortunately, simple harmonic motion is going to be changed out for something called damped harmonic motion. So instead of being described by just a simple sine or cosine, what we see with damped harmonic motion is that the amplitude just keeps dying off. And if you're interested in the math, that amplitude is dying off as an exponential decay. So it looks like something like that, an e to the minus t. So the amplitude is dying off, but we still see the period of the sine or the cosine function that would describe the simple harmonic motion of the object. Okay, so without friction, we could expect it to continue oscillating back and forth. With friction or drag, unfortunately, the amplitude is going to die off until it eventually stops moving. Okay, all right. What I mean by a linear restoring net force, if you remember when we first looked at Hooke's law, it said that the spring force is minus kx, where k was just the spring constant, the stiffness of the spring. And that little minus right there meant that it was a restoring force. Whatever you do to the spring is always going to put a force in the opposite direction. Like if you stretch the spring down, then the net force on the mass is going to be up. It's trying to bring it back to this equilibrium position. And if you compress the spring, then the net force is going to be down. It's always trying to go back to equilibrium. That's what we mean by a restoring force, okay? But Hooke's law doesn't just apply to springs. This means that any object where the net force is restoring, so it has a little minus there, and linear with respect to the displacement from equilibrium. So you remember x was just how far you stretched or compressed the spring. So any object who has a net force that is both linear with respect to the displacement and restoring towards equilibrium is going to be in simple harmonic motion. So that means we'll be able to describe the position, velocity, and the acceleration as sines or cosines. Okay, so I'm looking at this little GIF at the bottom of a satellite going around the Earth. So this is a periodic motion, right? It's very predictable. It's going to repeat that motion over equal time intervals. So we would call that uniform circular motion. But is that also simple harmonic? Well, what I would need to do is look at the net force on that satellite. And if I were to draw a free body diagram of the satellite, it's really just the force of gravity. At any time, the force of gravity is pointing towards the center of the Earth. And the force of gravity is big G times the mass of the Earth times the mass of the satellite divided by the distance to the center of the Earth squared, right? So that's GMM over R squared. Well, the mass of the Earth isn't changing. The mass of the satellite's not changing. And even the distance to the center of the Earth, if this is a circular orbit, is not changing. So what's interesting about this net force on the satellite is it's actually constant, which means it's not a linear restoring force. It's not trying to come back to some equilibrium. This is just a constant net force that is keeping this object in uniform circular motion. So unfortunately, while it is uniform circular, it is not simple harmonic, just for the mere fact that the net force is not linear and restoring. But there's something really interesting about uniform circular motion and its relationship to simple harmonic motion. They're very closely related, even though they're not the same thing. Because if you imagine an object in uniform circular motion and you tried to describe just one component of the motion, so instead of looking at it moving in two dimensions, if you tried to describe just the horizontal motion, or just the vertical motion, then we know that we could take this object and imagine this red dot when it's in this position, and if I measure the angle from the positive x-axis, we know that we could describe the horizontal position of that object as r cosine of theta. And we can describe the vertical part of that as r sine of theta. So what you're seeing here with the blue dot is we have an object in simple harmonic motion, but notice how it lines up under the red dot at all times. So that red dot in circular motion, if you only track one dimension of its motion, that particle is going to be in simple harmonic because it can be described as a cosine, or the vertical position can be described as a sine. So there's definitely a really close relationship. Uniform circular motion and simple harmonic motion are not the same thing, but we use them a lot of times to translate rotational motion to translational motion. So if you think of like the pistons in a car engine, they're oscillating in simple harmonic motion, but they're driven by a crankshaft that is in circular motion. So very well related, and it's going to help us build these equations for simple harmonic motion. Okay, so first I just want to go through some new vocabulary, but I forgot about this slide. I apologize. There's a really interesting thought experiment, and that is if you were to drill a hole through the center of the Earth and then drop somebody through it. And lots of famous scientists have given their piece on this. Neil deGrasse Tyson has a really good solution to this problem. And it turns out that the person who drops through the hole is going to be in simple harmonic motion. But as you notice here in this GIF, the period of that person oscillating through the center of the Earth is identical to the period of this satellite. And it turns out the solution, this person's period is about 84 minutes. So if you drop through that hole, you're going to go all the way to the other side of the Earth and back in 84 minutes. And for a low Earth orbit satellite, the period is roughly 85 to 100 minutes. So we see again that marriage between something that's in uniform circular motion and its relationship to something that's in simple harmonic motion. Okay? But as I said, we're going to do some new vocabulary. Period, we know, is the time for one complete oscillation. So this is like seconds per oscillation. Oscillations is a countable number, right? So it's not a real unit. So we describe period as just being seconds, but it's really seconds for one oscillation. And an oscillation is just a complete cycle, right? So it has to do everything that it's going to do in its cycle before it repeats itself. Frequency is just the inverse of period, so 1 over period. So if period is in seconds, then the unit of frequency would be 1 over seconds, which we call a hertz, Hz. Okay. Truly, though, this is the number of cycles per second. But again, cycles, oscillations, those are countable numbers. We really don't need to report them. So we say hertz or 1 over seconds, but that's really the number of cycles completed in 1 second. So maybe you've seen hertz before. When you buy a TV, it says 60 hertz. What does that mean? Well, it means that the image on the screen updates 60 times every second. Okay. So 60 cycles per second. Amplitude is just the maximum displacement. So the maximum displacement, and for us, that's going to be the maximum displacement from the equilibrium position. So I want to do a quick demo. I've got this spring mass oscillator set up here, and I'm going to use this program. This is Pasco Capstone, and I've got a little motion sensor set up right here, and it's going to track the vertical motion of this spring oscillator. So whenever I hit record, it's going to set that position to 0. So that's our equilibrium position. And then I'm going to set it into motion. Okay. And what I have here is simultaneously a position, velocity, and acceleration versus time graph. Okay, so go ahead and hit record. Right there, it says it's not moving. I'm going to lift it up to a positive amplitude, and I'm going to let it go. So now we have it oscillating back and forth. So I'm looking at that blue. That is just the vertical motion of the object, but I'm also getting something very similar for the velocity and something very similar for the acceleration as well. So if I stop recording that, I feel like we have enough data there. What I have is very clearly sines and cosines for all three: position, velocity, and acceleration. And I'm going to go ahead and move my time. So we'll call this the beginning of the experiment. I'll move my time so that I'm starting there at a positive amplitude. And then I would say that I could describe my position as a cosine, right? Because if it starts at a positive amplitude, it would be described as a cosine. Now, I do have the equation sheet here, and you notice on the equation sheet, they have position as a cosine, but they also have position as a sine. So the interesting thing is, all that matters is when you decided to start your stopwatch. In my experiment right here, I have it set up where I started my stopwatch when it was at an amplitude. But you could imagine that, if somebody else walked in and started recording their data as it was passing through an equilibrium position, then they could use this as their graph for the position versus time, and they would describe that as a sine function. Not a problem. All that matters is, what did it look like at t equals 0? Am I starting to measure as it passes through equilibrium, or am I starting to measure when it was at an amplitude? I prefer personally to start it at an amplitude, because that's how I did this one, right? I lifted it up to a positive amplitude and then I released it. So I'm going to describe my position as a positive cosine function, okay? But notice what that does to my velocity. They drag right along with my position graph, and these times are related. The same moment in time on the position graph is that same moment in time on the velocity graph. So if I describe the position as a cosine, how would you describe this velocity function? So it starts at 0 and it goes negative. So that would actually be a negative sine wave. And then if you go to the acceleration versus time, since it starts at a negative amplitude, that looks like a negative cosine. So again, the conditions for simple harmonic motion is that the net force on this object was linear and restoring. And because that was true, we got cosines and sines for all of our position, velocity, and acceleration. But they're also even a little bit more related than that. I said that the position function was a cosine. So what I'm going to do is I'm going to say amplitude, so however far I pulled it back, times the cosine. And from my equation sheet, I'm seeing that they write that as 2 pi times the frequency times t. So basically, the shape of that graph is a cosine. Okay, so it starts at a positive amplitude and it oscillates back and forth. And then we saw that the velocity was a negative sine wave. And it's also going to have 2 pi f t, but the difference is it's not oscillating from a maximum position to a minimum position. It's oscillating between some maximum speed. And then the acceleration function was described as a negative cosine, so 2 pi f t, and it's not oscillating between maximum velocity and minimum and high negative velocity. It's oscillating between some maximum acceleration. Okay, so what are some observations we can make from those graphs? I like to keep an eye on what's happening when I'm at an amplitude. So when I'm at my furthest position, the velocity looks like it lines up with 0, right? So if I go to my highest position there, I've got a velocity that's really, really close to 0, and I've got an acceleration that's also a maximum, but it's at a negative, right? So when I'm at the highest position, it stops moving, and the acceleration is strongly negative. Well, that's because it's a restoring force, right? It's really trying to bring it back to equilibrium. And then as I'm passing through equilibrium, right here, as I'm passing through equilibrium, I'm at my largest speed. It happens to be in a negative direction because it's traveling downward, and there's no acceleration there. Why? Because I'm at equilibrium. And remember that the net force is linear with respect to the x, so x to the first power. And then I blow through the equilibrium position. I get to a negative amplitude. Again, the velocity stops. And now I have a really large positive acceleration because it's going to try to bring it back to equilibrium. So we see that oscillation in all three of those kinematic variables, so position, velocity, and acceleration. So I can say that, sorry, I can get the lights back on, maybe. I can say that V max occurs when x and a are 0. I can also say that a max occurs at the same time as the position is a maximum and the velocity is 0. So at the amplitudes, The velocity is 0. The acceleration is in the opposite direction of the position, and they're both maximums. And as I'm passing through equilibrium, there's no acceleration, and the velocity is a maximum, okay? So we can do a lot with that. We're also going to relate this 2 pi f to that uniform circular motion so we can get a better understanding of what that 2 pi f means. But that's it for now, and thanks for watching.